Welcome back. This is Dr. Jason Harrington, and today we'll be talking about substitutions and transformations. Now, in this particular section, we're going to have three different types: homogeneous equations, Bernoulli equation, and equations of the form dy over dx is some function of a linear transformation of x and y. Now, before we begin, all of these different substitutions work in the same similar manner. So here's the general substitution principle for all of these ODEs and how to solve them. So just keep this in mind as we start working through them. The first one is important, is you want to identify the type of equation. One of the biggest problems that people have with difference equations is that when they're in the homework called Bernoulli's equation, then they know to use Bernoulli's substitution. But when the test comes, or when they meet some generic ordinary difference equation off the street, then they don't know what to do. So make sure that as you practice your homework and practice anything, make sure that you can identify why are we using that particular equation. The second thing is, you want to, after you also determine the appropriate substitution or transformation, then you rewrite that original equation in terms of the new variables. Then you solve the transformed equation, and then you transform it back into the original variables. So keep all this in mind as you show you these different examples. All right. So the first example I want to do, I'm just going to do it, and then I'm going to show you later on how to recognize it, is first of all, I'm going to solve for dy over dx. So that means that I get dy times x is equal to, and I can just write this as y minus x dx. And then if I divide everything through by x, then I get, and dx too, I get my dy over dx is going to be equal to y divided by x minus x divided by x, which is just 1. And this is basically the first trick that we're going to learn, but we can see that this is now just a function of the ratio y over x. So now if I just say, let's let v equal to y over x, then we have this function, and we have g of v is just equal to v minus 1. Now, that's pretty much the hardest part, really, is being able to identify that if it's a function of y over x, then I can just let v equal y over x. And now if I solve for y, I just get y is equal to v times x. And then if I use the product rule, then I get dy over dx is equal to the first times the derivative of the second, that's just dx over dx, which is just 1, and that's just 1, plus the second times the derivative of the first, which is dv over dx. And we also have that dy over dx is equal to g of e, just from our construction of g. Remember, that was just from our construction of e. So if I put this substitution inside my dy over dx, then I have v times 1, which is just 1, plus x dv over dx is equal to g of v. Now what makes this cool is that that's now separable, which makes that easier to solve. So then I want to put all the v's on one side, so I'm going to have, let's see here, I'll have x dv over dx is equal to g of v minus v, and then if I multiply both sides by dx, then I'm going to have, I'll just do this one over here, then I'll have x dv is equal to g of v minus v times dx. And if I want to get, now I'm not quite done obviously because I still have v's over here with x's and v's all together. So in order to make this separable, what I have to do is divide everything through by x and 1 over, so let's try this out, 1 over g of v minus v dv is equal to 1 over x dx. Now on the left hand side, remember what g was. Don't forget g. G was up here. G is just v minus 1. So on the left hand side I have 1 over v minus 1 minus v dv is equal to 1 over x dx. When I integrate both sides, the left hand side just becomes, this I'll just write integrate both sides. So when I integrate the left hand side, I just get negative v, because it's just negative 1 is the only thing that's left over. And on the right hand side, I'm going to get just the natural log of the absolute value of x plus c. Now recall that note v was just equal to y over x. So when I make my substitution, y over x is just going to be a negative minus the natural log of x plus a constant. Then we can just solve for y, equals to, almost forgot my little equals to, can't forget that little guy. So that means I'm going to get y is equal to negative x natural log of the absolute value of x, and then this I can just write as equal to minus c times x. And that is our answer. So really the hardest part about this whole thing was, again, just recognizing the substitution. Once you make the substitution, don't forget to put this back into the original equation. You definitely want to be taking derivatives somewhere. So let me just talk about what I did and when does this trick even work, right? How do you know you can use this trick? It should be a very important question. So what we have is a homogeneous equation if we say that if the right-hand side of the equation, dy over dx, f of x comma y, can be expressed as a function of the ratio of y over x alone. Just like in the last example, as soon as I wrote it as y equals to y over x, then I could work with it. Then we say that the actual equation is homogeneous. Now we say we have a homogeneous function of degree alpha. That's precisely when a function f of x, y is said to be homogeneous of degree alpha if I put in a t x and a t y, then the t can be factored out, maybe some multiple of t. And again, that alpha doesn't have to be just an integer. It can also be irrational or even to the pi, for example. That's a little bizarre, but that is possible. So a first order ODE we can recognize is homogeneous if both of these are homogeneous in the same way. All right, now the idea behind why this actually works is pretty simple. Suppose that we do have a function where I can put in t and tx and ty, and I can factor out a t to the alpha. Then if I let t equal 1 over x, then what happens is if I let t be 1 over x, then the first one becomes just 1, and then this becomes y over x, which is now a function of just y over x. And again, I can factor out a 1 over alpha to x to the alpha, leaving that with just f and x and y. Now, another thing I want you to note here is that so far we've always been leaving v equal to y over x when this happens, in this particular case. So in this case, we let v equal to y over x. But note that if you write it as a function of the other way, like so for example, what would happen if I let t be 1 over y? If you get a function like x over y, comma 1, by letting t be 1 over y, then this also works. So as long as you can write this as a function of 1 over this now y to the alpha, f of x comma y, then and this happens in this case, then you would let v equal to x over y. Basically, you're just looking for a ratio of y over x or x over y in every single case. So now this question says, I want to solve this guy. So I have two functions, and I'll rename them the same, just like in all the other sections. I'll call this one m of x comma y, and I'll call this little function here n of x comma y. And the thing that a lot of people tend to forget, and make sure you practice this, you call the first one in front of the dx the m, and the one in front of the dy an n. There's actually some homework questions that are pretty easy to solve as long as you label them correctly. Sometimes they'll put the dy first just to confuse you, but it's the same process. Just label the one in front of the dy as n, and the one in front of the dx as m. So the first thing I'm going to do is I want to check to see if I can even do this technique. If I check m of t x comma ty, then that just turns into ty quantity squared, which I can write as t squared times y squared. But remember, y squared was just m, so that's just t squared times m of x, y. And the second one, I have n of tx comma ty is equal to, this is going to be tx squared minus tx times ty. The first one I can factor out a t squared. Well, I can factor a t squared from both of these little guys. And then I'm left with x squared minus xy, which is the same thing as saying t squared times n of x comma y. And both of those tell me, because they're both squares and everything matches up nicely, that this is now homogeneous of order 2. So it's a homogeneous of order 2. And that tells us that this method actually works, that we can do this. So the next step I'm going to do is I'm going to say, let's let v equal to y over x, which is the same thing as just saying x times v is equal to y, or just y is equal to x times v. And then when I take the derivative of this, I'm going to have the derivative of y with respect to x is now going to be equal to the first times the derivative of the second plus the second times the derivative of the first, which is just 1. And you can also just rewrite this as saying that if I multiply everything through by dx, then I can say dy is just equal to, I'll write the v one first, v dx plus x dv. All right, so that's the equation that I'm going to use for my substitution. So when I come over here, I have y squared dx plus x squared minus xy dy equals 0. Alright, so the next thing I need to do is do all of my substitutions. So the first one you'll notice is the dy. So the dy, remember, was v dx plus x dv. And also y is equal to x times v, and I'm going to substitute that back into the first y as well as the y squared. So you want to make sure that everything gets converted over into x's and v's. So then after our substitution, let's see what we have now. We're going to have x times v quantity squared dx plus x squared minus x times v, x times xv times v dx plus x dv. So that was from the substitution earlier. And the right-hand side remains 0 for this term. Okay, so now we just need to clean it up a little bit with some algebra. Is to write this as x squared v squared dx plus x squared minus x, I'm getting that from this term up here, x squared times v, and then in the parentheses I'm going to get, still keep this the same. Now what I'm going to do is I'm going to take each term and I'm going to divide each term by x squared to make it simple, because I can factor out this x squared into the front, and then also I have an x squared on that term there. So once I do that, and I'll factor out the x squared for e so you can see it, I'll be left with 1 minus v for this particular term, and the rest of it is v dx plus x dv. And here I've crossed out the x squares. Alright, so now what I want to do is I'm going to be distributing this to each term. So I'll be taking this first term, 1 minus v, and multiplying it by v dx. I want to take this term and then multiply it by 1 minus v times x dv. So you can see that right here. And you'll notice that I just kept the x dv together. Alright, now one thing that you'll notice is I have these two terms here, v squared dx plus 1 minus v times v dx. So my next step is to basically combine these two together. So I'm going to have v squared plus v, that's from this guy being distributed, minus v squared. And I went ahead and distributed the v to each piece and factored out dx plus x minus vx. So again, what did I do is I just distributed that over. So you can see that distribution occur. And now we can simplify some of these terms here. For example, the v squares, they're canceled. So now we're left with just having this equal to v dx plus x. I can factor out an x from this. I don't know why I distributed it and then factored it out. But again, you get the same result. I'm trying to make it as simple as possible. And sometimes you can play with the ODE a little bit to see what notation and what factorization works best. Now the neat thing is that when we're at this particular step, this equation is now separable. So what we can do is we want to put all the x's on one side and all the v's on the other. So in this case, I'll keep the dv on the right-hand side by just simply moving this over. Now when I move this over, it's actually minus this, but I can replace that minus with v minus x. So I just change the 1 minus v to v minus 1. Then what I will do is I need to get rid of this x, so I'll bring that over to the other side. And then I need to move this v to bring this to the other side, which turns into 1 minus v dv. And that is what we'll solve on the next slide. I want to keep going with this, so there is more after this slide. Alright, so let's go back to where we left off. We left off here, 1 over x dx is equal to 1 minus 1 over v dv. Alright, now let's see how we can handle this little monster here. So on the left-hand side, we're going to have the natural log of the absolute value of x. And on the right-hand side, we're typically going to have v minus the natural log of the absolute value of v. I don't know why I just put parentheses down, But again, parentheses are free, so I try to use them as much as I can. They're the only things in life that are free. You can never go wrong with parentheses. So I always like to add them, plus C. And now what you have is, you have this equation, but you recall that V is just equal to y over x. Okay, so if I plug that in there, and also I'm just also going to assume, and this happens sometimes in some homework problems, in a class like this, they typically assume that everything is nice. So I'm going to assume that the y over x is greater than 0, and y is greater than 0, and the x is greater than 0. Everything works out nice, and I don't have to worry about negative, taking the absolute values. And if I make that assumption, I'm just going to get the natural log of x is equal to v minus the natural log of v plus a constant. And then I put in my substitutions everywhere I have that v. So I put it here and then here. So that's going to turn into the natural log of x is equal to v, is equal to y over x minus the natural log of y over x plus c. Now we can clean this up a little bit. I can write this as the natural log of x is equal to y over x minus, and I can split up the natural log by saying the natural log of y minus the natural log of x plus c. Again, I just like my free parentheses. Once I distribute the minus sign, you're going to get the natural log of x is equal to y over x minus the natural log of y plus the natural log of x plus c. And then what you'll notice is that the natural log of x's are on both sides. You cancel those guys out. And you can bring the negative natural log to the other side. But really you're just left with the negative, just saying the natural log of y minus y over x is equal to a constant. And that's your final answer for that. Cool. So basically this just had a lot of algebra and manipulation there to simplify it. But the idea was the same. Alright, so now the next equation that we have to work with is the Bernoulli equation. I always love these names because they always sound really cool. Bernoulli. But a first order equation that can be written in this form, dy over dx plus p of x times y is equal to some function of x, and this is the real big difference here, is that you're going to have y to some power. Okay? It can be any real number. It can be a half. It doesn't have to be an integer. Then we say p and x are continuous. If p and x are continuous on a to b, some interval, and n is just any real number, then we call that a Bernoulli equation. And the idea for this is that we're going to let v equal to that y to the n minus 1, or y to the, sorry, I meant to say 1 minus n. That is what you do when you see a Bernoulli equation. And you do the same process and you make the same substitutions that we did before, just in a similar manner. Alright, so let's figure out why and how this works. By the way, first step is, if this n is equal to 0, then it's already linear, and you're done. So if it's just 0, or if there's no y's there, you don't have to worry about it. Now the first thing I'm going to do is I'm going to divide each term through by n, and now you get your new equation, which is y to the negative n dy over dx plus p of x times y to the 1 minus n. And you can see that what you really want to do is you want to get rid of this term by substituting that. So then if you let v equal to that, and that's actually a typo there, that should be y to the 1 minus n, because this is the substitution you want to make there. That tells you what you want the substitution to be. So if you make the substitution, v is equal to y to the n, take its derivative, and you see this is the derivative. You end up having the 1 minus n come down in front. Then you subtract 1, which gives you to the negative n, and then you get dy over dx. And when you separate this out, then you're going to get, you want to keep the y's on the right hand side, and the dv over dx is just a number, 1 over 1 minus n. Then you substitute it back into the ODE. If you substitute the dy over dx back in, let me actually highlight that. If you substitute this back into the original, this whole term just becomes 1 over 1 minus n dv. And this little guy just becomes v. And then you have a q of x. And that turns into something that's completely linear. And you solve it just like it was linear. Okay, so let's work it out. And again, I don't usually memorize a bunch of formulas for this. But over here, the first thing I'm going to notice is this is my y cubed, right? And so what I'm going to do is I'm going to divide everything through by y cubed. Then you end up having y to the negative 3 times dy dx minus 5. This turns into, and since there's already a y there, just y to the negative 2 is now just equal to negative 5 halves x. And that's the first step that I do. Now in the second step, recall that we have, when I say divide by, oh, that's cute, I used y as by as well as the y cubed. That's totally incorrect. I just used that y too many times. But we have y to the cubed. This is our n. So we say n is equal to 3. And so what you say is I want to let v equal to y to the 1 minus n, which is equal to y to the 1 minus 3, which is equal to y to the negative 2. Now, in all honesty, I don't really memorize all that. I literally just look at it and I say, well, what is this? This is my y right there. So you can either memorize the formulas or you can simply just look at it and say, okay, that's the term right there by itself is going to be my v. So once I have v is equal to y to the negative 2, I take its derivative with respect to x to both sides. So I get dv over dx is equal to negative 2y to the negative 3 times the derivative of the inside, which remember the inside's y, so that's dy over dx. All right, now I want to bring that negative 2 to the other side. Also, that kind of makes it a little bit easier. So now I'm going to have, whoops, that is going to equal to negative 1/2 dv over dx is equal to y to the negative 3 dy over dx. Cool. Then 3, I just substitute everything I know. So I'm going to substitute. Now, let me write out what we have so far. So far we have y to the negative 3 dy over dx minus 5 y to the negative 2 is equal to negative 5 halves x. Okay, so if we have y to the negative 3 dy dx, the first substitution I'm going to make is going to be this guy here. And that is just going to turn into what I have here. That's going to be negative 1/2 dv dx. All right, now I also have right here y to the negative 2. And if I go back, y to the negative 2, that's just v. So I have minus 5v is equal to negative 5 halves x. All right. Now, I don't like all these fractions, and neither should well, anyone, and negative signs to boot. That's horrible. So if I can multiply everything through by negative 2, so I'm going to multiply by just negative 2 to every single term, then I'm going to have dv over dx minus, well, plus, that's right, plus 10v is going to be equal to 5x. All right. Now this is in fact linear. So let's solve this. I'll bring up the next page. All right, so what was I left with? I was left off at dv over dx plus 10v equals 5x, and this was linear. So I'm going to let my integrating factor be mu of, and now I want mu of x is equal to e to the integral of 10 dx. So don't forget I'm using this little term here to figure out what my integrating factor is. So that means that mu of x is just equal to e to the 10x. Now I hope this works out nice. So if I multiply each term by this, then I have e to the 10x dv over dx plus e to the 10x times 10v is equal to 5x e to the 10x. And remember the whole point of this, remember the whole point of it being linear, is that in the integrating factor, by the way, this is the, I should have probably spelled that out, int factor that we want to use. So that is our integrating factor. And if we did the integrating factor correctly, then this should rearrange now into the derivative of x. So that should be e to the 10x times v. And remember, I always like to check myself for the first few times just to make sure people understand it. But if I take the derivative of this piece here, I should get that. So if we do that, I'm going to have the first times the derivative of the second. That's what I have, the first times the derivative of the second, plus the second, which is just v, times the derivative of the first. And the derivative of e to the 10x is just 10 e to the 10x. So that works. That's what that comes from, right? It's undoing the product rule. And the right-hand side just remains the same. All right. Now, we want to integrate both sides. So now let's int both sides. And we have e to the 10x v is equal to, and on the right-hand side, I'm going to get x over 2 e to the 10x minus 1 over 20 e to the 10x plus c. That's basically, you can do that by integration by parts. Yes, integration by parts would have to do that. That's wrote down. Now I have to divide every term through by e to the 10x to get v by itself. So now I get v is equal to x over 2 minus 1 over 20 plus c to the e to the negative 10x. Now what I'm going to do is I'm going to recall that v was equal to y to the negative 2. So now when I make the substitution back into v, where v is now equal to y to the negative 2, I get that the actual solution is going to be equal to y to the negative 2 is equal to x divided by 2 minus 1 over 20 plus ce to the negative 10x. Now because I didn't solve for y, I'll just leave this as an implicit solution. And the reason why I want to leave this implicit is because if you look at this, what's going to happen is this is really just going to be 1 over y squared, 1 over y squared, and in order for me to solve for y, not only would I have to take the reciprocal of the right-hand side, but then I'd also have to take the square roots. And when you take a square root, you have to make a decision. Is it positive or is it negative? Right? Because when you take the square root of both sides, you have to put in the plus or minus. And so you have a lot of complications there. So usually to ease the complications, you can write it as an implicit solution, because then that covers all cases. All right. Hopefully some people made it this far, but now this is our last one of this particular section for our substitution. When the right-hand side of the equation dy over dx is equal to f of x comma y, if we can represent this, f, in terms of some linear combination of a, b, and just a and b, and then a constant at the end, plus c, then we have a function g written in this term. Then we make this substitution here, that's going to be our substitution, and that turns the equation into a separable one. So let's take a look at this, work this one out. So we have dy over dx is equal to 1 plus e to the y minus x plus 5. So here's what I do. I have dy over dx is equal to 1 plus e to the y minus x plus 5. And I'm going to take this little guy up here, right there, and I'm going to say, let's let, it doesn't matter what you call it, I'm going to let it be called u, is equal to y minus x plus 5. And now when I take the derivative of each term through by x, I get du over dx is equal to dy over dx minus 1 plus 0. All right. So now, if I solve for dy over dx, then I'm going to get du over dx plus 1 is equal to dy over dx. So now that's our substitution. So this little guy turns into u, and the left-hand side, that just turns into du over dx plus 1. Now once I make that substitution, I get du over dx plus 1 is equal to 1 plus e to the u. Oh, and look how cute this is. Just the ones cancel. Oh, this is really beautiful. The ones cancel, so nice. And I'm left with this nice little separable equation. Du over dx is equal to e to the u. That's nice and separable. Oh, it's such a nice, I always like it when problems work out this nice. Then you get e to the negative u, du is equal to dx. Once I integrate both sides, then I'm left with negative e to the negative u is equal to x plus a constant. And then I can rewrite this as negative e to the negative, and then don't forget this little guy up here. This is my u, and I want to put him right back down here. So don't forget the parentheses. So that's going to turn into y minus x plus 5 is going to be equal to x plus a constant. Now here we could have solved for y. If we solve for y, I mean basically if it says just solve, this would be an answer. So I'm going a little bit above and beyond. But if I want to solve for y, in the numerator, or in the exponent I should say, is negative y plus x minus 5. And then I bring the negative to the other side, minus c. I take the natural log of both sides, and I get negative y plus x minus 5 is equal to the natural log negative x minus c. And so then I bring everything to the other side, so then I have negative y is equal to 5 minus x plus the natural log of negative x plus c. And then if I make everything negative, I get y is equal to, I'll just put the x first, x minus 5 minus the natural log of negative x plus c. Now this is also a good demonstration of what we mean here. This, we would say, is an explicit solution because it's written in terms of just y. Right? It's written in y, and I can just plug in numbers for x and figure out what y is. Here, if I just left it like this, that's called an implicit solution because I just left it. You know, I can't just start slapping in things and expect things to pop out. If I slap in x's, I still have to do a lot of manipulation to figure out what the y is. So that's the difference between an implicit and explicit solution. All right. The next guy that we have, this is going to be, again, we're going to be left with dy over dx is equal to sine of x plus y. And I know what you're thinking. You're going, gosh, if this was just anything other than x plus y. So let's do it. Nothing's holding you back. Gravity's holding you down. I don't know what's holding you back. So here's what you're going to do. You're going to say, let's let, and in this case, I'll just call it v, just because I'm not really good with coming up with names. V is equal to x plus y. Then my dv, and again I'm taking the derivative with respect to x to all sides, it's just going to be 1 plus dy over dx. So then I put the 1 over on the left, and I get dv over dx minus 1 is equal to dy over dx. So now I got to make all my substitutions. This inside just turns into v, and then dy here turns into this little dy guy right here. So on the left hand side I have dv over dx. Almost forgot that little one guy. Man, sometimes he's hard to remember. Sine of v. And now if I bring the plus 1 to the other side, I'm left with the dv over dx is equal to sine of v plus 1. Uh-oh. It's looking a little bit more crazy. Then, if I divide everything through by sine of 1 over sine of v plus 1 dv is equal to dx. Okay, that looks... Alright, so we need to do something. So again, you got to use a little bit of algebra tricks, or tricks that you know from Calc 2. But here's what I'm going to do. V plus 1. What I'm going to do is I'm going to multiply the top and the bottom by sine of v minus 1 divided by sine of v minus 1. dv equals dx. And let's see if that helps us out any. So the numerator just turns into, what do we get here? Sine of v minus 1. And the bottom is the difference of two squares, which is just sine squared v minus 1 dv equals dx. Now, did that help? Well, if I rewrite the bottom, I can rewrite the top and the bottom by writing 1 minus sine of v over 1 minus sine squared v. Oh, nice. I can use some Pythagorean properties here. Over dx. That gets turned into, the denominator turns into 1 minus sine of v divided by cosine squared of v dv. Hey, don't get mad at me. I don't design these things. Dx. It's nice. Now, if I divide each term through by cosine, then I'm left with secant squared v minus tangent v, and what else is left? Tangent v times secant of v. And that's my dv. is equal to dx. Okay, now let's integrate both sides. Now the good news is that these are nice integrals. So on the left-hand side, we're going to get tangent of v minus secant of v is equal to x plus c. And then we have to remember to put our substitutions back in. So for this, don't forget that v is equal to x plus y. So once we do that, then we're going to get tangent of x plus y minus secant of x plus y. Actually, this didn't work out. Actually, this worked out nicer than I thought. Sometimes you get really lost in all these trig identities. It takes a while. But this one actually worked out quite succinctly. So it just helped a little bit to remember some nice little trig rules that you learned from Calc 2. Cool, and that's it. I hope that made sense, and hopefully I'll see you next time.